Hey everybody, it's Scott from Redmond Tutoring.com, and this week it's exam season here in Montreal, so I'm going to go through a quick exam review question of the motion of charged particles in electric and or magnetic fields. I'm going to look at 4 different scenarios, and first I'll just show them to you really quickly so that you can take a look at them, and then you should pause the video and give it a try. So in the first scenario, we have a constant uniform electric field going off to the right. And inside that field, we have a positive particle. So I have a plus in there showing that it's positive. And this charged particle has a velocity at the instant shown that is upwards. And so the question that you need to be able to answer is to describe the motion of that charged particle in that electric field. So that's part A. Question B is quite different. Instead of an electric field, we have a magnetic field, but it's also going off to the right. So we have a constant uniform magnetic field going off to the right. In this case, we have a negatively charged particle in the middle, and it also has an initial velocity, and its initial velocity is downward. And again, we need to describe the motion of that particle in that magnetic field. For the third one, part C, we actually have a combined electric and magnetic field. In this case, the electric field is uniform, constant, and pointing down. And the magnetic field is also uniform and constant and pointing down. And we have a negatively charged particle with an initial velocity that is upwards. So we describe the motion of that particle in that combined electric and magnetic field. And the fourth one has an electric field pointing inwards, as if you had maybe a negative charge, like the electric field that you would see from a negative charge. In this case, we have a positively charged particle, and at the instant shown, it has a velocity going straight up. In each case, the challenge to you is to describe the motion of the charged particle. So right now, the best thing you could do would be to pause the video and just quickly jot these down on paper. It doesn't have to take very long. And then when you're ready, resume the video and then compare what you predicted to what I say is true. So the first scenario had a positive charge moving perpendicularly to an electric field that's off and to the right. And so if you remember for the electric field, when you have an electric field like this, then you might remember that the electric force is equal to Q times the electric field. And in this case, we have a positive charge. So that means we'll have positive something times E. And really what it means is that the force is going to be in the same direction as the electric field. Now, you might remember from mechanics, Newton's second law, which went something like the net force, F net, is equal to m times a. And if you divide both sides by m, you'll get that the acceleration is equal to the net force divided by m, which is the mass. Since mass is a positive, we don't have any negative mass, this means that the acceleration is also going to be in the same direction as the force and the field. Now, I always draw acceleration as a double arrow just because I do not want to forget and treat it like a force on free body diagrams. Anyway, what that means then is that after every instant, the velocity is going to change because of the acceleration. And so this particle is going to actually follow a parabolic path. So this particle will be deflected to the right and follow a parabolic path or a parabolic trajectory. For part B, we have a negatively charged particle traveling downwards through a constant uniform magnetic field that's to the right. And this is a bit trickier. You might remember that you have to actually consider the three-dimensional aspect of this because the magnetic force is equal to Q times V cross B, which means that the force is actually perpendicular to V and perpendicular to B. And we need to do the vector cross product or apply the right-hand rule in order to get that. So if we're going to actually do just the cross product of V cross B to start, I'm going to treat the negative charged particle separately in just a sec. So V cross B, in order to apply the right-hand rule for V cross B to get the direction that comes out of that cross product, I personally start with an open palm, so a flat palm, like a knife edge palm. And I start then with my fingers in the direction of V, so that would be pointing down. Then I need to turn my hand so that I can curl my fingers and bend them at the knuckles so that they're pointing in the direction of B, which is off to the right. And then my thumb is actually pointing out of the screen. So V cross B, when you have V down and B to the right, that gives a force that is actually out of the screen, and I represent that with a circled dot. Instead of saying a force, I should say that gives a result that is out of the screen. But in this case then, the particle is a negative particle. So what I end up getting is that the force F of B is equal to some negative value times this direction, which was out of the screen, which means that the force direction is actually going to be into the screen. Now, this is a kind of an unorthodox way to show this kind of problem. Typically, when you have a particle moving in a magnetic field, they would actually show you the magnetic field either going into the page or out of the page. In this case, I'm showing X's to represent that the magnetic field is into the page. And then you might still have a negative particle, and you can have it moving in whatever direction you want. So I imagine it going off to the right. In that case, right-hand rule, I'd start with my fingers to the right, curl them inwards towards the page, towards the direction of B, and my thumb points up. But it's a negative particle, so the force has to be going in the opposite direction, and the force on that one would be going down. And this is honestly the way that you would normally see it. But it's good for your brain to actually look at different things, and the same concepts still apply, and it's the perfect time. I'll have to admit, physics teachers love to test your understanding of these concepts by throwing in just a little wrench like this, by having B going off to the right. Because the force on this particle is into the page and the velocity is downwards, this particle is actually going to go in uniform circular motion. And at the point shown, it's going downwards, but it's going to go downwards and then eventually circle into the page and then upwards and then circle out of the page. Essentially, it's rotating in a vertical plane, and if we were to see the motion, it would go down and then back up and then back down again. And the axis of rotation is the same, is horizontal along the same direction as B. In this third example, we have a negative particle with an initial velocity moving upwards, and this particle is in a combined electric and magnetic field. So there's an electric field and a magnetic field. And the electric and magnetic fields are both pointing in the same direction, down. So in this problem, we have to consider both types of force. So I'll use some color coding and do the electric force on red, which is going to be Q times E. Now, in this case, Q is negative, so that means that the electric force is going to be upwards. For the magnetic force, we have the magnetic force is equal to QV cross B. And in this case, V and B are parallel. One way of writing this equation in terms of just the magnitude is QVB sine theta. In this case, V and B are 180 degrees, so we'd have sine of 180 degrees, which is 0. So the magnitude of the magnetic force is 0. It doesn't really matter what the direction would be because the magnitude is 0. So in this case, there is only one force. The net force then is the sum of both of them. But since the magnetic force was 0, really the net force is just the electric force, and that was upwards. So in this case, the electron, or the negative charge, I'm assuming it's an electron, but it doesn't have to be. In this case, the negative charge is going upwards, and because the net force is upwards, therefore the acceleration is also upwards. So in this case, the particle will accelerate upwards, speeding up with no change in direction. And now it's time for the last example. Now remember, this electric field was pointing inwards. It's what you would get if you had a negative point charge. But the scenario we were given had a positive charge off to the right with a velocity going upwards. Now, there's no magnetic field in this case, so we can really just apply the force, or the equation for the force from the electric field as Q times E. So at the instant shown, then the force is going to be to the left. This is a positive charge, so it's not going to change direction. Now, that force then is going to cause an acceleration to the left as well. As the particle moves then, I'll just sort of draw that out, the velocity is going to be changing according to the acceleration. Remember, acceleration is just a change of velocity over time. So this means that as the particle moves along, the velocity changes, and the trajectory is going to represent that change. By the time the particle goes around, say, about an eighth of the circle, the velocity will have changed quite a bit. Now, remember, the field lines are just representative. They don't show they're not meant to be the only places where the fields are. It's just that we use them as a tool. The electric field is actually everywhere. So by the time the particle reaches this position, the velocity will have changed. I can call that v prime. Now, the velocity is up and to the left at this point instead of just being straight up, because all the way along, this particle has been accelerating in the direction of the electric field, which is towards the center. Now, you may remember that acceleration towards the center is centripetal acceleration, and this is actually a way of getting uniform circular motion from an electric field. And this can seem a bit counterintuitive at first, because we're used to seeing uniform circular motion as a special case with a particle moving in a magnetic field. But if you think of an orbit, like the moon orbiting the Earth, or you could imagine in this case maybe a proton orbiting an electron, is kind of the opposite of what we'd normally see. But anyway, if you have a positively charged particle that's attracted to a negatively charged particle, then you could have this positive particle orbiting the negative particle. And if you just think about something like that, where you have an attractive force and one object orbiting another object, then it makes more sense. It seems a little less counterintuitive to be describing uniform circular motion. And that's all that this is. I'm Scott Redmond, and I help students pass physics. I really hope this video was helpful to you, and if so, please like it in YouTube to let me know. And if you happen to be among the people who are writing an exam in the next few weeks, then good luck with your exams.